IOT. And the other thing is on Thursday, we won't have a class, but I'll give you an exercise to do. I need to take my son to the clinic for checkups and immunization. He's 2 months old, so I need to be there by 9. So I want to make the class and also be at the clinic. But I'll give you an exercise on Node-RED so that during that time you can do the exercise. So today we'll just cover the distributed systems. We won't have a case study this week. We'll have one next week. So next week we'll have a case study. Yeah. So just to repeat, on Thursday we won't have a class. I'll give you an exercise so that you can do it that time. The exercise will be on Node-RED. So I'll upload the exercise in the e-learning in the course of today or tomorrow, so that you're able to do it on Thursday. Yeah, so I think a good number have joined. So we can start the class. So I'll just share the screen. So I hope you're able to record. So I'm also recording, but I hope you can also record by yourself. So if you are recording, you can just start recording. So today's topic is on distributed embedded systems. It's not as difficult as last week's, but you need to pay attention. It will be a little bit longer than the rest. Maybe it will take maybe 45 minutes. So we will just, these are the objectives for today's class. So we'll introduce the concept of distributed embedded systems. So, and then we look at the networks, embedded systems. So networks for embedded systems. So what kind of topologies are you likely to be dealing with when you're designing an embedded system? And then we look at we'll go now deeper into modeling a network. So for example, how many layers? So we try to model a distributed embedded system network using the OSI framework. So yeah, we'll cover those in this class. So these are the objectives. So we'll start with the definitions, of course. So what is a distributed system? So a distributed system is a set of nodes which are connected to a network, and they are cooperating to achieve a common goal. So here we have two concepts. So there's the nodes. So we'll also define what a node is, and then there's also the aspect of a network. Okay. So what is a node? So this is in context to distributed systems. Okay. So a node in this context is a small complete entity on a network. So it's composed of a control unit. So the control unit can be a microprocessor or a microcontroller, whatever it is, yeah. And then it has a sensor and actuator, and then it has a communication network interface. So that is a node in a distributed system. Then a network is a system of interconnected nodes. So these definitions are in the context of a distributed system. In another context, they might mean something else. But in this context, this is how we define a distributed system. Okay. So, so what are the components of a distributed embedded system? So we have the hardware components. So that is the sensors, actuators. We'll have a class where we'll cover sensors and actuators. So don't worry if you don't understand what they are. Then we have the control unit. So last week we covered the microcontroller and microprocessor. So I hope by now when you hear those terms, you at least understand what you're talking about. And then we have the communication network interface. So this one we are going to cover today deeper. We are going to cover it deeper today in the next few slides. And then so control unit we covered last week. Sensors and actuators will cover it in the next few weeks. Okay. Then we have the software components. So there is drivers, network protocols, and real-time operating system, which is optional. Okay. So drivers are just firmwares. They are read-only programs. So there's really nothing to cover there. What we'll cover today is the network protocols. Okay. In depth. So we'll cover network protocols in depth. Okay. So so what are topologies? So we have centralized. You can see there is a chart. Okay, so let me turn off my camera. Okay, so we look at the topologies, network topologies for an embedded system. So there is the centralized. So we look at for centralized, ad hoc, dispersed, and distributed. So our goal is to cover the distributed embedded system. Okay, so the first three is just for us to understand that there are other types of topologies, but our aim for this unit is to cover the distributed embedded system. So for the centralized, this is how it will look like. You'll have the control unit or the CPU, and then you have your sensors and actuators connected to it. Okay, so sensors can be temperature sensors, humidity sensors. Actuators can be maybe motion sensors, can be maybe a switch or something. But you have one CPU, and then everything else is connected to that microcontroller or microprocessor. Okay, so there are advantages for this, and there are disadvantages for this. So the advantage is that you're efficiently using the processor. Okay, so you most probably will maximize the potential of that processor. Okay. The other advantage is that it's easy to set up. So you're just connecting sensors and actuators to a single, uh, to a central point. So it's easy. Then it's easy to configure the software because you only need to configure software in that CPU. So if you're uploading a program, you'll upload it to a single CPU and then it runs. So it's easy to configure softwares. The problem is that it becomes difficult to expand, especially um, when the resources of that CPU are depleted. So for example, if this CPU can only support maybe 20 sensors and 20 actuators, and then now you want to add more, maybe the system you're designing maybe now requires 50, it will be difficult to expand. It means you need to maybe get rid of that control unit and get another one which has more capability. Okay. So it's difficult to expand in future. So that's something you should keep in mind. Then it requires a powerful processor. So the more actuators and sensors you add, the more demanding they'll be on the processor. So you require a very powerful processor. Then the cabling is very chaotic. So this picture here shows how, for example, your cabling can be very chaotic because everything is sort of connected to one single point. So it becomes very chaotic. Okay. Then we have the ad hoc. So ad hoc, it means you expand by just adding nodes on top of the existing ones. Okay. So for example, this one here, this node here, you can see it is connected to two more. Okay. But this one here is only connected to one. Okay, so you just adding, so you just add, so there's no formula, you just add the nodes to existing ones without any predefined uh, design. Okay, so it's easy to expand, as you can see. So if you require maybe more actuators and sensors, you just need to add another CPU which comes with those actuators and sensors, and then you just extend the existing ones. Okay. The problem is the mapping or overloading. So some CPUs will be overloaded. For example, one might be you might extend one with maybe 10 other nodes. So that node will be overloaded. And maybe you extend another node with only one or two nodes. So that node will not be overloaded. Okay. Then the cabling is a little bit complex because now you have to keep track. So anytime you're expanding, you have to keep track of how you're expanding your network and everything. So it becomes a little bit uh, difficult. You can see Ian is asking a question. Does the middle CPU that connects them has its own sensors? Yes. So this one you're talking about the centralized or the ad hoc? If it's centralized, then the CPU connects to all the sensors and actuators. If it's ad hoc, it means every CPU comes with its own actuator and uh, and the sensors. Okay, so as you can see here, each CPU comes with its own, and you can see it doesn't limit. Okay, so this is like just having uh, 10 centralized CPUs, and then you just connect them together. Okay, so one CPU, for example, can have 20 actuators and 20 sensors, and then you connect them to, you sort of interconnect them into a network. So you still could be overloading one CPU with so many sensors and actuators. So that is also another way of looking at it. And another CPU can have very little sensors and actuators. Okay. So this is the ad hoc. Okay. So we have another question. Can CPUs share sensors and actuators? No, they cannot. So yeah, they cannot share. So for example, this sensor here cannot be shared by this CPU. Okay, so this sensor can only be used by the CPU it's attached to. Okay, but this CPU can control. You can sort of write a program that allows one CPU to control the sensor of another CPU. It's possible, but using it, no, I don't think so. Then there's the decentralized. So decentralized basically means you sort of have you don't have a single point of connection. So this one you have a bus, a central bus, and then everything that is supposed to be connected into that network is connects to the network through the bus. Okay. So you have so many CPUs. So every time you want to expand, you have a central bus, you just be connecting into that bus. Okay. So this one loads, it allows you to load balance the network, but the main disadvantage is that the bus is a bottleneck. Okay. So for example, if let's say the bus has a bandwidth of let's say 8 bits. So let's say let me see if I can share screen right board. So let's say the bus has a bandwidth of 8 bits. So maybe this is the size of the bandwidth of the bus. Then you maybe have a CPU here, a control unit maybe. It has its actuators and sensors, okay, and the sensors. And then inside it has a CPU and maybe the bandwidth. So here we've said it's 8 bits. Maybe this CPU, this one here, maybe it has a bandwidth of 16 bits. Okay. You realize that this CPU will sort of be it will be required to operate at 8 bits when it can operate at 16. Okay, so it means that bus will be a bottleneck. It will cause it to operate at uh, at a lower performance that it's capable of. Okay, so a bus can be a bottleneck. So that's one way of looking at it. So if you have more powerful CPUs, it means they can't operate at their maximum uh, at their peak performances, but they have it at the peak performance of the bus. Okay. And then also, if maybe this bus can only support, let's say, a maximum of, let's say 32. So the size maybe of the total data that can pass at one time, yeah, maybe a maximum of 32 kilobytes. So it means if you have so many CPUs such that they produce informations that are bigger than 32 kilobytes, it means some information will be lost. Okay, so those are two ways of looking at the bus as a bottleneck. Okay, so a more powerful CPU, or also in terms of the size. But the beauty is there is efficient balancing of the network. Okay. Then I want you to take note for the first three, the centralized, the ad hoc, and this decentralized. One CPU can be connected to as many sensors and actuators as possible. Okay. So you decide, like for example, you want one control. For example, you want your control unit to maybe measure temperature, humidity, and maybe soil pH, one CPU. So you'll have like 3 sensors on that. Yeah. And if you want it to do more than 2 tasks, maybe you'll have more than 2 actuators. So for the first three, all the three, one CPU can have as many sensors and as many actuators as possible. So when you come to the distributed, uh, it's the same as decentralized. The only difference is that one CPU can only have one sensor and one actuator, or one actuator or one sensor. So it's either one sensor, one actuator, or a pair. So it can't have more than 2 sensors. It can't have more than. So that implicitly means that one control unit can only perform one task. Okay, so it can only sense one thing. It can only execute maybe one task. Okay, so that allows you to have a modular design. Okay, so you can be able to sort of break down your system or design your system into a modular. So so if you want, for example, to measure soil, only one node will be responsible for that. Okay. If you want to measure maybe a temperature, only one node will be responsible for that. Okay. So that means if, for example, you realize that your system is not getting accurate measurements of maybe temperature, you know which node to look at. Okay. So that is the beauty of modular design. Okay. This is what we want to look at deeper, distributed embedded systems. So I see I have a question here. The last point on one actuator, one sensor. Yeah, so for distributed, so let me repeat. For the distributed, it means one node. So for example, this one here. So let me try to draw it, yeah, so that I give the options, yeah. So for example, if you have this as your node, So the first option is that it can only have can actuator. Okay. Or the third option is it can have one sensor and one actuator. Okay. This is what I mean. So what is not acceptable is, for example, you have a node and then it has maybe two actuators, okay? You have one actuator, you have another actuator, okay? So this is not acceptable. This is what is acceptable. Or you have another node and then maybe it has two sensors, okay? Or more than two, sorry. Maybe it has two, three, or four. Or you have one, then it has a sensor, an actuator, and maybe another sensor. Okay. So this is so this part here is not acceptable. Okay. Okay. So I think Ngugi understands now. So that is what I mean. Okay. So back to the slide. Okay. So there's an advantage for that, and that is the modular design. Okay. But still, since they are connected to a central bus, it means they are limited. The performance of your system is limited to the capability of the bus. So if you have a small bus, it means your system can only do so little. If you have a very capable bus, system can do so much. Okay, that is clear for the topologies. So I have another question here. Does the one task per node also make it more expensive to implement? Mm, I don't know if it's a thing. Maybe the you're asking is in terms of maybe you need more components to achieve maybe a simple task. Yeah. For example, if you want maybe to design a system that measures temperature and maybe humidity, and then you just turn on the fan. If you use a distributed system, it means you'll need three nodes. Yeah, one for measuring humidity, and then actually two. You can have one for measuring temperature, one for measuring humidity, and then one for humidity maybe has one actuator for turning on the fan. Yeah? But if you use a centralized system, it means you can have one node that can do all the three. So maybe in terms of hardware, yeah, it's more expensive. But in terms of designing, it's cheaper because you'll see when we go to the next slide, it will be easier to troubleshoot. It's easier to design. It's easier to actually make it easy for someone else to understand what you're designing. What is, I think it's the modular design. So that's the reasoning behind, so that it allows you to design, to have a modular, to design your embedded system in a modular way. Okay. So what are the benefits of having a distributed embedded system? So the first one, of course, is the modularity. Okay. So since functionality is divided among the processors, you don't need one powerful processor. You need several less powerful processors. And in the long run, it's cheaper to have less powerful processors that performs a task than one powerful one, which is more expensive than the three. Okay. Then there's easy integration. Okay. So since one node does one task, you can have different vendors. So for example, this is now when you're designing now a commercial product. Yeah? You can have one vendor taking care of one phenomena, then another vendor taking care of another phenomena. For example, you can have, for example, company X that maybe are doing very good systems on maybe measuring temperature. So you can have one node designed by company X. Then you have company Y, which do a very good job at designing fans. Okay, so you can have another node that implements the design for company Y. So if the system for the node Y is the system for company X, okay, so it can still measure the temperature. Okay, so it allows you to have systems, okay, without them uh, maybe interfering with each other. So if you had a centralized, it means if the node for company X fails, then it means the node for company Y most probably won't work, okay, because they are fed from the same node, okay. Then scalability. So this is basically because of the bus. So it's very easy to add nodes, okay. So it's easy to scale, it's easy to expand the network, okay, and it's easy to also reduce the network without interfering with any other node, okay. Then there's a fault tolerance. So I've alluded to this. So when you have a bus topology, it means basically it's not based on a centralized system. So even if one node fails, the other ones will still continue working. Okay, so that's the beauty of a bus topology. Then flexibility. So this one is almost the same as easy integration. Okay, so you can integrate different, and then you can also update affecting update one node without affecting the others. Okay, so easy is very important. Okay, so it's easy to troubleshoot failed nodes. So if one, because it's modular, you'll know that this function is not working. If one node fails, and then it's about failure of the bus itself. Yeah, if the bus fails, then everything fails. So that's why we are saying the bus is a bottleneck. That is the biggest disadvantage. Yeah. So Jesse, I hope that answers. So the bus is it's the biggest advantage and also the biggest disadvantage. It's a bottleneck. Yeah. Then B. Yeah. So whatever Jesse is asking is here. So it's easy also to identify a broken bus. Okay. So if the bus is fails, then maybe it fails at a particular, maybe between node X and node. It's easy to know it's easy to know that at this point, this is where there is a broken link. Okay, we'll see. I think the next slide will sort of try to demonstrate that and you'll be able to see. And then since, so this one processor is each node should be node, not processor, can diagnose its own sensor and actuator. Okay. So this is for, I think, for all the networks, this is possible because a sensor and actuator is connected to one control unit. Okay, and then the last one, each node can determine which other node is alive through message feedback. So this is what will allow you, which is what will allow you to detect a broken bus, the point of break, the point where it breaks. Okay, so for example, if you have, this is your bus down here, then you have, this is your node, you have node 1, 0, 1, 2. Okay, so if the bus breaks at this point, so message feedback, for example, allows these nodes to communicate to each other. So this node can actually sort of like pinging. Yeah, so if this is node 0, it tries to ping the nodes that are surrounding it. So only node 1 to ping. So it knows that it's surrounded by node 2 and node 0. And node 2 is only. So if this network, you'll see node 0 cannot communicate to nodes, so that there's a problem here because node 1 also cannot communicate to node 0. So it's easy to identify the point where the bus has a problem. Okay, I hope it's clear. So that is the advantage of distributed embedded system topology. Okay. So this is an example, a real life example. So for those who didn't know, a car is a very good example of a distributed embedded system. The current generation of cars, okay, not the old generations, the current ones, yeah. So for example, you have a power window, which has its own maybe processor, okay. So if this fails, your car will still move, okay. You have your transmission. If this fails, your power windows will still work, okay. You have your anti-lock brakes, you have the engine. All these are sort of different, but they are connected through the same network, okay. Okay. So a car is a very good example of a distributed embedded system. So class exercise. So write this one down. You do it at your own time. So I want you to research on the drawbacks of a distributed embedded system. Okay. So from the character or the disadvantages. Okay. Yeah. So we are halfway through. Any question? Okay. So now we go to the communication. So we'll first of all look at two types of communication, how communication can be handled. So keep in mind, from now on, what we are looking at is in a distributed embedded system. So in a distributed embedded system, how can take place? Okay, so there are two ways. So there's the event triggered. Okay, so this is a reactive embedded distributed system. Okay, event triggered means, for example, you have, for example, here we have a node, for example. So when the user presses a button, then it's place. So that knows information through the bus, and then maybe something happens. Okay. So it's triggered by an event, triggered by the user, reactive to the environment. Okay. So for example, you have your sensor. Your actuator detects something. Okay, maybe the temperature drops. Then it sends that signal to the node, and then the node now sends a message to the bus, maybe to the next node to maybe turn on the fan or something. Okay. Hope it's making sense. Yeah. So this one reacts to the environment. So it's event triggered. So the basically the messages inside the bus. So if I can uh, let's say so let me say we have our bus here. So this is our bus. So what you're talking about is the messages coming, the messages that are going and coming. Okay. So maybe you have one message. This is a message, and that is the direction that they are going. Yeah. So you have maybe this message is from this node. Maybe sending it to this node here. Okay. And maybe another node here is sending another message to. So you have this here, you have this maybe coming here, okay? Then you have this maybe sending it to another node, maybe here, okay? So you have this trying to communicate with this. So what you're talking about is these messages inside here. So how they come, how do they exist, how do they come to life, okay? So they can be event triggered. Then it initiates this message, okay? I mean, it's clear. Right. To the slide. Yeah, so that is event triggered. Okay. So time triggered basically means each slot for it to communicate. Okay. So for example, the so maybe if there are 5 nodes, a node is given a second to, if it has any information, to pass it through the bus. Okay. So at that, no other node sends information. And then after 1 second, maybe the first second is node 1, second node 2, second, and after all the nodes are finished, it goes back to node 1. I don't know if it means only one node is communicating. Okay, so this can be known as a real-time distributed embedded system. Okay, so it's given a time slot. Okay, for the reactive, you realize that it's possible for messages to collide. Okay, so one node can send a message at the same time as another node, and then they meet. When they collide, it means messages are lost. Okay, so later in the slides, you'll see why these two are important and how you can take care. So there is a solution for the reactive, and there's a solution for the real time. Okay, so that is so these are the two ways in which messages can be sent through the bus. So now what you want to do is to model the communication. So into an OSI model. Okay, so there's a question here. What is there any moment that a certain node is prioritized? Now that, so Julie is asking a question. So is there any moment that a certain node is prioritized? So that one depends on the protocol you're using. Okay, so we'll see that in the I think in the next few slides. You'll see how to take care of that. Okay, so you can decide to prioritize master slave. So you have one node as a master, then so it becomes a priority. So anytime it wants to send anything, it has to clear the bus and everything. So we'll see that there in the next few slides. So now we want to model the distributed embedded system network into an OSI a model. Okay. So for us to do that, we need to define a few terms. So the communication network interface mentioned. So have our node. So here you realize that I've not put the sensors and actors, but they are there. So we want to just go now deeper into the communication. What we are to model it. Okay? Okay. We'll have like so compute microprocessor. Okay, with your microcontroller. Then you have your control network interface, and then a communication controller. Okay, so this is the communication network interface is the one that connects your microprocessor. The communication controller is the one that connects this node to the bus. Okay, so it's sort of like a physical uh, connection for the communication network interface to the bus. Okay, sort of like a firmware or something like that. Okay, so if you want to communicate, it means for node 1 to node 2 to communicate, it means information comes from the host computer, goes through the communication network interface, and then it goes through. So it goes through like the red arrow shows, yeah, through like this, and then it goes into the next node, and then the microcontroller can now process the information that it has gotten. Okay. So this communication network interface can be put in the transport layer of the OS model. Okay. So if you were to put it in a model, it will be in the transport layer. Okay. But now the problem with the OSI model, it has 7 layers. Okay. And when it comes to the distributed embedded system network, some layers are totally useless. Okay. So we need to get rid of the useless layers. We need to redefine other layers. Okay. So if you're just to sort of like plug it in into the OSI layer, then the control network interface will appear at the transport layer. Okay. But we can't use this model because there are certain layers that won't be doing anything. Okay. So these are, I think I mentioned this. So if we use the OSI layer, so these are the disadvantages. So payload. Okay. So for example, it will require us to do routing at the network layer. Now, routing is totally useless if you're working with a bus, okay? Because bus, the most common method of communication is broadcasting. Okay, so you just broadcast, all the nodes get it. The one that is supposed to act on it acts on it. The other nodes discard the message. I don't know if it's making sense. For example, so let me just try to. So if this is your bus, okay, and then you have this is node. This, let's say you have nodes here. Okay, so 2, 3, and 4. Okay, so let's say node 1 wants to communicate to node 2. Okay, so it will just broadcast. It will send that message in the bus. So since everything is connected in the bus, every node will get the message. Okay, every node will get the message, the same message. So if this message is meant for node 2, then node 2 will react. The others will just discard the message. Okay, so really there's no need for routing, because routing means you have a specific sender and a specific receiver, and any other node on the network is not supposed to see that message. Okay, so you realize that is completely for a bus topology, the network layer is completely useless. Okay. Okay, and then there is the back-to-back. Okay, so these are the issues. So that's why we can't choose the OSI layer as it is. So we need to sort of redesign it, okay, or collapse it for the case of a distributed embedded system. Okay. So if we collapse it, we'll have only 3 layers. We'll have the application layer, data link, and the physical. Okay. So the physical is where the communication connecting the node to the bus. Then we have the data link. Okay. So this is where we'll now put some intelligence, what Julie was asking. So if we don't want this node to send a message and another node is transmitting, but maybe they clash. So this is where we'll put our intelligence, collision detection, or make these nodes. So if this node is supposed to be, that information will be the data link layer, okay? Then we have the application layer. So anything that is maybe requires more processing will be on the application layer, okay? So the transport is now, we rename it to the data link. You remember in the OSI, the CNI was on the transport layer, but now we rename it to the data link layer. Okay? So that now what I'm going to do is just go into details about the three layers. So what is the task of the application layer? What is the task of the data link layer? What is the task of the physical layer? Okay. So the physical layer. So so it takes care of the control area network. Okay. So this is, for example, the bus. So the connection. So that connection is called a control area network. Okay. So the messaging that is implemented is the broadcasting. Okay. So this is the form of exchange that is executed in a bus. Okay. So there is no need to perform routing. So just broadcasting. Now the main disadvantage with broadcasting is the collision. Okay. So two nodes can send a message at the same time, and then the messages collide, and then both messages are lost. So that will be taken care of in the data link layer. Okay. So we have the data link layer. So what does it do? So this addressing is not routing. Okay. So this is just a low level addressing. Okay. So for example, if I want the node for the, for example, the node for a fan to go on, then addressing that I'll put there is maybe specific to that. I don't know how to explain it, but it's not routing. It's a low level of just trying to get the node responsible to act. So the other nodes just reject that message. Okay. Then the data link will also have the logical layer. So just in case the messages collide and it's lost, then it will get an error. Okay. So the node will get an error and then maybe try to retransmit again. Okay. Then it will implement this media access. This is the intelligence. So how does it know that the bus is free so that it sends a message without it colliding with another message? Okay. So there are different types of media access control. So there is the master slave, which Julie was alluding to. So you have one node as master, then the other ones as are slaves. So when the master wants to speak, the slaves listen. Okay. Then you have the TDMA, time division. So this one is best for the real time. Remember the one that has time slots. The nodes are given time slots. Okay, so that's one way of minimizing collision, because at a given time, only one node will be allowed to transmit a message. Okay, then there's the collision sense. Okay, so this one is for the reactive. So you can have collision sense with collision detection, then collision avoidance, bitwise arbitration. I believe you've covered this in your networking class, yeah? So there's nothing new, okay? So this is the logic that will be implemented in the data link layer for the bus topology, okay? Then the application layer. So this one does the high-end tasks, okay? So for example, client server, if your data link implements a master slave, then you'll have a client server model in the application layer, okay? If it implements a collision carrier sense detection, then you'll have a publisher subscriber, okay? So this publisher subscriber will meet it later. It is very important. It will become maybe a pillar for maybe some of your projects. So for now, just know that it's something. Yeah? Then a message protocol, maybe converting message maybe from one format to the next so that the node can understand. Then clock synchronization, maybe if you're doing a time division, you need to synchronize the clocks of each node so that the time slots are not confused. Okay. Hope it's making sense. Yeah. So this is the exercise. So write it down. So I've given you two exercises. So the first one is for the drawbacks. The first slides before the exercise will give you This one, the second half of the slides will give you a hint on how to tackle them, okay? So look at the three layers, the protocols I've mentioned. Some will require you to sort of like go deeper into a particular protocol so that you understand how exactly it works. For example, carrier sense, multiple access with collision detection, you need maybe to understand exactly how it works and so forth, okay? So as I said, these questions are very important. For those that I don't answer in class, just know that most probably they may appear in your CAT or in your exam. So it's good that you try to do it so that when you see a similar question, maybe different, slightly different, you know how to answer it, yeah? So that you don't say you were never taught. Anyway, any questions? So that is the end of today's class. I think it has been a short one, but I hope you've understood a distributed embedded system. So any question? So as I said, on Thursday, I won't be there. So I'll give an exercise and then on Node-RED. So I hope you are able to install. I hope you are able to install. So the enrollment key is so someone is asking about the enrollment key. So let me just write it down. So the enrollment key is yes, IOT. That is the enrollment key. So I'll put the exercise in the e-learning, the one that you'll do on Thursday. So I hope you're able to install Node-RED. I hope you're able to play around with the Arduino web interface. So I'll put exercises for Node-RED on e-learning so that you try them out during the Thursday class. I won't be there. And then, yeah, that's it for this week. So next week, we'll start on IoT. And then next week, we'll have a case study. Okay. So if there's no other question, I think we can stop there. You have a nice day and safe, and enjoy the rest of the day. Okay.